All right, so this should really be our last video now for section 4.3, entitled Primes and Greatest Common Divisors. So a first important fact here is if you have the equation A equals BQ plus R, here A, B, Q, and R are integers, positive integers, then the GCD of A and B is the same as the GCD of B and R. Yeah. So this kind of equation here, I'm underlining in red, that looks like your division algorithm. Remember the division algorithm? That was really important. Earlier in, I think, 4.1, it says if A and B are positive integers, well, we didn't use actually A and B, we used A and D, I think. Yeah, A and D are positive integers. Then what you can do, you can take A and divide D into it. So D goes into A and you get a quotient plus a remainder. And you have to remember that the remainder, one important thing, the remainder here is always less than the divisor D and always greater than or equal to 0. That's called the division algorithm. So we pretty much, this underlined equation here, I'm going to actually put a box around it. That looks just like the division algorithm equation, except rather than a D, we have a B for our divisor. So what that says that the GCD of these underlined numbers, A and B right here, those are the same as these underlined numbers, I don't know if I can get them in the right color, B and R. The GCD of the yellows are equal to the GCD of the greens in the equation. That's going to be really important. So here we're going to write down what's called the infamous Euclidean algorithm. This is super important. We're going to be making good use of this. So the Euclidean algorithm. And it says this: if A and B are positive integers with, let's say, A greater than B, and let's say I take A and I divide B into it, and I get a quotient, let's call it Q0, plus a remainder, let's call it R1. I'm doing the division algorithm between A and B. I get a quotient Q0 and a remainder R1. Let's say the remainder is not 0. So in this case, the remainder is positive if it's not 0. Remember, it's always less than your divisor B. Okay, so now let's take R1, the remainder, and divide it into the divisor B. So I'm going to have B, and I'm going to divide R1 into that. I'm going to get another quotient, let's call it Q1. And then we're going to get a remainder, let's call it R2. So I took R1, divided into B, I got a quotient Q1 and a remainder R2 with, so our remainder, according to the division algorithm, our remainder R2 should be less than our divisor this time, which was R1. And let's say our R2 turns out to be positive. So not 0, but positive. Let's say we decide to do this process once again, where we take R2 and divide it into R1. So we're taking R2, our new remainder, dividing it into R1. We're going to get a quotient, let's call it Q2, plus a remainder, let's call it R3. So R2 was divided into R1. We got a quotient Q2 and a remainder R3. R3, that's our new remainder, should be less than our new divisor, which was R2. And it should be greater than or equal to 0. But let's just say it's not 0. Let's say it's still positive. Let's continue this procedure. Eventually, we'll get down to a step where we're taking, let me see, we're going to take in Rn minus 1, and we're going to divide it into an Rn minus 2. And we're going to get a quotient, Qn minus 1, and a remainder, Rn. And let's say this Rn, this remainder Rn, remember it has to be less than the divisor, which in this case is Rn minus 1. Let's say this Rn is still not 0. Let's say it's still positive. And then finally, we take our last step, where we take our Rn, our remainder Rn, and we divide it into our Rn minus 1. We get a quotient, let's call it Qn, and let's say we get a remainder of 0 this time. So in this case, the remainder is 0. So if you do the division algorithm repeatedly like that, over and over and over and over again, and eventually your remainder turns out to be 0. Eventually it'll have to be 0. Let me put commas here, comma, 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 comma. So you do this over and over and over again. Eventually, after you do it enough, your remainder will be 0. Then the GCD of A and B has to be equal to Rn. What was Rn? It was your last positive remainder that showed up. Where was that? That was right here, right? This was the last positive remainder. Now let's think through this. Why is that the case? Why must it be that last positive remainder? Well, if you go back and you look at our fact at the top, it says that the GCD of A and B is the same as the GCD of B and R. So if we apply that to what we have here, the GCD of A and B, so let me write this down here to the side. This is kind of a little proof of our theorem. The GCD of A and B must be equal to the GCD of B and R1, right? B and R1. These two greens. So I have these two greens now, right? B and R1. So the GCD of B and R1 must be equal to the GCD of R1 and R2, using that fact again from the top. So the GCD of B and R1 is equal to the GCD of R1 and R2. So we have, let's use a different color. We have R1 and R2 here. So the GCD of R1 and R2 has to be equal to the GCD of, use that fact again, R2 here and R3. So that's equal to the GCD. R1, R2 is equal to the GCD of R2, R3. All right, so you keep that process repeating. Eventually you'll have that's equal to, so dot, 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 that repeats. You'll have that's equal to the GCD of Rn minus 2 and Rn minus 1. GCD of Rn minus 2, comma, Rn minus 1. So eventually you get all the way here, underline. So this is going to be equal to the GCD of Rn minus 1 and Rn, GCD Rn minus 1 and Rn, until your very last step. What color am I going to make that? I'll make it cyan color. So you'll have, well, red. You have here Rn minus 1 and Rn. So their GCD is going to be equal to the GCD of Rn and 0. And what's the GCD of any positive integer Rn and 0? It's going to be 0, right? The largest thing that divides both of those is 0. So that's how you get, oh, sorry, Rn. Said the wrong thing. What's the GCD of Rn and 0? It's Rn. Get this to right. Okay, I'll just write Rn here. If I can get it to right, there it goes. Yeah. And it's just using that fact over and over and over again, that fact at the top. That's pretty cool. So, the Euclidean algorithm enables you to find the GCD by repeating the division algorithm until you get your very last positive remainder, which will be your GCD. So, this is useful for solving something known as Bezout's identity. So what is Bezout's identity? We want to talk about Bezout's identity. It says, if A and B are integers, both not 0, then there are integers x and y such that AX plus BY equals the GCD of A and B. Or in other words, sometimes you hear this said, the GCD of A and B is a linear combination of A and B. A linear combo. You might hear it called a linear combination of A and B. Now this is the equation that we mean by a linear combination. The GCD is a linear combination of A and B. So doing the Euclidean algorithm and working backwards from that is going to allow us to solve this equation for x and y. So let's work some examples doing this. So use the Euclidean, if I can spell Euclidean correctly, here we go, erase, Euclidean algorithm to find GCD of A and B. After we find the GCD of A and B using the Euclidean algorithm, we're going to work backwards. To express the GCD of A and B as a linear combination of A and B. Or in other words, to solve Bezout's identity for x and y. There we go. We're going to have our first pair of numbers. We're going to have 1,439 for A, and for B, 1,529. So I'm going to do the Euclidean algorithm. Euclidean algorithm. So starting with our A, 1439. No, not 1439. 14,039, I believe. Yeah. 14,039. And I'm going to, let's see, divide B into it. 1,529. We're going to get a quotient plus a remainder. So let's see. 14,039 divided by 1,529. I get a quotient of 9 plus a remainder of, let's see, 14039 minus 1529 times 9, 278. All right. So I'm underlining these numbers. I'm going to take 1,529 and divide my new remainder, 278, by it. Underlying these numbers, I'm going to get a quotient and a remainder. So 1,529 divided by 278 gives me a quotient of 5 and a remainder of, let's see, 1,529 minus 278 times 5. Get a remainder of 139. So now I'm going to take 278 and divide my new remainder 139 into that. Underline those. I'm going to get a quotient and a remainder. 278 divided by 139. Hey, that's 2. I get a remainder of 0. So I got a remainder of 0, so I'm pretty much done the Euclidean algorithm. So remember what your GCD is. Your GCD of A and B is going to be your last positive remainder, which was here at 139, right? 139, that's your GCD. Now, the whole point of using the Euclidean algorithm to find the GCD, it's not the quickest way to do it, but it's going to allow us to solve the Bezout equation. So let's write down. So we're going to solve the equation 14039x plus 1529y equals the GCD 139, right? We're going to solve it for x and y. So I'm going to start, what I do, I start with my last positive remainder equation and get 139 by itself. So in this case, your last positive remainder was 139, so we're going to write that by itself. That's equal to, well, what I have to do, I have to take 1529, I'm going to underline that, and I'm going to have to subtract 2 times 278 to get 139. So basically I subtracted 278 times 5 from both sides of that next to last equation. All right, now I'm going to leave those numbers underlined, 278 and 1529. They're kind of treated like variables, and the red 2 is treated kind of like a coefficient. So we want to check our numbers that are underlined, right? We have, what, 1529, 278, and we want to look at the smaller one that's underlined, that's 278, right? 278 is not our original number A or B, right? It's neither A nor B. So we want to update that 278 with something else. So we're going to go to the next equation above the last one we used. So we had one with 139 on the end. Now we're going to go to the one here with the 278 on the end. And we're going to replace 278 with 14039 minus 1529 times 9. So I'm going to leave the 1529 alone, underlined. I'm going to leave the minus 2 alone. And in place of 278, I'm going to put, using that top equation, 14,039, underline that, minus 9 times 1529. Underline that 1529. All right, so I replaced 278 with 14,039 minus 9 times 1,529. Now this is all equal to 139. Okay, so I need to clean this up. I got 1,529. I'm going to distribute the negative 2 where I keep the blues kind of like variables. So I'm going to have negative 2 times 14,039. And when I distribute the negative 2 to the other term, I'm going to get a positive 18. I'm going to leave the 1,529 kind of like a variable. So I'm not going to actually modify the 1529. Just leave it like that. Equals 139. Now I got to combine my 1529s, right? So I'll write first the larger negative 2 times 14,039. So I'm writing the larger blue number first. So 14,039, I write that one first and has a coefficient of negative 2. Now the 1529s, when we combine them, we're going to have 19, right? You got 1 copy plus 18 copies. So if you don't see a 1, you can imagine there's a 1 right here, right in front. You have 1 copy of 1529 added to 18. So you're going to have plus 19 copies of 1,529. So we're treating these blue numbers kind of like variables here. We don't want to actually multiply 19 times 1529 out. We don't want to actually multiply negative 2 times 14,039. We want to keep the blue numbers blue and just mind the coefficients. So the question is, are we back to our original numbers yet? So look at 14,039 and 1529. Yeah, those are the original A and B numbers. So since we have those, we basically have solved our equation, right? We have here AX plus BY equals the GCD. So it looks like here for X, we have negative 2. It's right there. And for Y, we have 19. So that's it. That solves Bezout's identity. So yeah, sometimes we get negative numbers. Now let's do another example. That one was rather short. We want to do a slightly longer example, because sometimes they do get long. Where do I have a problem? Okay, here's a problem. I have A equals 201 and b equals 111. So first we'll start with the Euclidean algorithm. To find the GCD, we're going to take the larger number 201 and divide the smaller number 111 into it. We're going to get a quotient of 1 and a remainder of, let's see, 201 minus 111 is 90. Underline those first two numbers. I'm going to take 111, divide 90 into it. I'm going to get a quotient of 1. I'm going to get a remainder of 21. Underline 111 and 90. Now I'm going to take 90. Yeah, I have enough space here, I think. 90 and divide the new remainder 21 into it. That's going to be, I believe, 4 plus a remainder of 6. I'm going to underline the 90 and the 21. Now I'm going to take 21 and divide 6 into it. We're going to get a quotient of 3 and a remainder of 3. So I'm going to underline my numbers 21 and 6. Now I'm going to take 6 and divide the remainder 3 into it. Make it a quotient of 2. With no well, you could say a remainder of 0. So when you get a remainder of 0, you know you're done. So the GCD here are these two numbers, A and B, is your last positive remainder, so 3. They have a 3 in common. It's the smallest, the greatest common divisor. The greatest common divisor. So the largest number that is a factor of A and B is just 3. So once you have that, you want to solve Bezout's identity, which is 201x plus 111y equals the GCD, which is 3. Sorry about that, I don't know what it's doing. And to solve that, we're going to take our last equation with the positive remainder, and we're going to get the 3 by itself. How do we get the 3 by itself? Well, you take, subtract 6 times 3 from both sides. So I'm going to actually keep the 21 underlined on the left side. I'm going to subtract a 3 times 6, underlining the 6 there. I'm treating these blue numbers kind of like variables. So now I look at my underlined numbers 21 and 6. I look at the smaller number 6 and see, is that one of my original A or B numbers? No. A and B are like 201, 111, so we're not there yet. So we're going to go to our next equation up from the last one we used. That's going to be the equation with the 6 remainder on the end. And we're going to replace our 6 that's underlined with 90 minus 21 times 4. So I'm going to keep 21 in front minus the red 3. And inside of the parentheses, rather than writing 6, we're going to replace that with a 90 minus, I'm going to say 4 times 21. And I'm underlining the 90 and the 21 here. All right, this is all equal to 3. Okay, so I got the same thing as what, 21. Distribute the negative 3, I got minus 3 times 90. And when you take negative 3 times negative 4, distributing on the second term, I got positive 12 times 21. Well, that's equal to 3. So I'm going to combine my like terms. Remember that this first 21 has a 1 in front of it, right? So you have, I'll do the larger blue number, minus 3 times 90. I like to write my large blue numbers first. And then I'm going to add the 21s. I got 1 21 and 12 21. That gives me 13 21s. This is all equal to 3. I'll combine my like terms. So now I got to check my two blue numbers. They're what, 90 and 21. I look at my smaller number, 21, and see, is that one of my originals? No, my originals are A, 201, and B, 111. So I got to take this next equation up with a remainder of 21, and we're going to replace the 21 in the equation with 111 minus 90. So I got here Negative 3 times 90, where did it go? Okay, negative 3 times 90 plus 13 times, instead of 21, I'm going to write 111 minus 90. It's using that equation, the second equation, right? Just getting 21 by itself by taking 111 minus 90. All this is equal to 3 here. So now I'm going to distribute the 13. So I got negative 3 times 90. Distribute the 3, I get plus 13 times 111. And we're going to have 13 times negative 90 would be minus 13 times 90 equals 3. So I'm going to write my 111 term first. So I'll have, you always write your largest blue term first. So I got 13 times 111. And I got negative 3 90s, negative 13 90s. That's negative 16 90s. All that's equal to 3. So am I done yet? Well, if I look at my blue numbers, my smaller number is 90. Right? My smaller blue number is 90. That's neither A nor B. It's not 201 or 111. So I'm not done yet. So I got to replace my 90 with something. So I go to my very first equation, working backwards. And notice that you can get 90 by itself by subtracting 111 from both sides of that first equation. So I'm going to replace the 90 with 201 minus 111. I'm going to have, let's see, 13 times 111. Minus 16, and here comes the replacement. In the blue parentheses, instead of a 90, we're going to have 201 minus 111. It's all equal to 3. And we're going to clean this up by distributing the negative 16. So I'm going to get 13 times 111 minus 16 times 201. When we distribute the negative 16 to the negative 111, we're going to get positive 16 times 111 equal to 3. And then we combine our like terms. Let's write the bigger of the two blue numbers first. So let's write negative 16 201 first, because 201 is the bigger one. And then for the 111s, we're going to have a positive 29, right? Because 29 is 13 plus 1, 6. So we got 29 111s equals 3. And I believe we are done because we have the A 201 and the B 111. Yeah. So if we're trying to solve the equation 201x plus 111y equals 3, we have done it. 201 is present in blue. X would have to be the red, negative 16. 111 is present in blue, and y would have to be the 29. That's it. Solution to the Bezout identity.